Now that we know something about how determinants work in the context of row reduction, let's see how this works out in practice with a few homework problems. As usual, I'll do some even ones and you can do the odd ones. So these are 3.2 exercises, and they start off just by saying what property is being shown here. It's worth pointing out, by the way, that this notation where the bars don't have the little corners on them, right? Normally, just when you're talking about a matrix, you'd have those little bars right there, those little things. But without those, just the straight lines, it sort of looks like absolute value. But in linear algebra language, that's the notation for doing the determinant. I don't think I mentioned that in the last video, so I just wanted to make sure you were aware of that. On number 4, for instance, they say what property is being shown here, and what did they do? It looks like they took -3 times the first row and added it to the third row, so that's why you get a 0 right here instead of the 3. Let's make sure that's what they were really doing. So -3 times 2 would be -6 plus 7 is 1. Yeah, okay, so it looks like they added a multiple of one row to another row, and they're pointing out that the determinant of this is equal to the determinant of this. So the property that's being illustrated there is the first one out of those. Oh, let's see, that's not it. Where is it? Yeah, out of these 3. So from theorem 3, we are illustrating property A. Likewise, oh, never mind. Sorry, I was going to say another one or two, but you will do the others from 1 through 4. Moving on through 5 through 10, I say go ahead and find this determinant by row reduction to echelon form. So this is only a 3 by 3. It wouldn't be that hard to find the determinant by cofactor expansion. But they say instead, go ahead and find the determinant by row reducing. So let's row reduce. We need to add -3 of row 1 to row 2. So that'll be my first step. When you're doing the homework, you don't have to write these out. I'm doing this for illustration purposes in this video. That would become 1, 5, -3. We'll get 0. See, -15 plus -3 is -18, and 9 plus 3 is 12. So far I haven't changed the determinant because I just did a multiple of one row added to another row, and I'm going to do that again for the third row. I guess it'll be also I'm also doing -2 of row 1 added to row 3 becomes the new row 3. So also that'd be 0. -10 plus 13 is 3. -2, so 6. -1. Okay, so far so good. The determinant of the original is equal to the determinant of this one. I could like do 3/18 of row 2 added to row 3. That would work. Actually, it wouldn't be terrible. But just to illustrate further, let's go ahead and swap row 2 and row 3. So I'm going to swap those 2 rows. 0, 3, -1, and 0, -18, 12. And keep in mind now the determinant of this is not equal to the determinant of this because I swapped 2 rows. And now it's equal to, it's the negative determinant of this. And it looks like the last thing I need to do to finish putting it in echelon form is I need to do 6 of row 2 added to row 3. Okay, so that becomes 0, 0. 6 of that, so negative 6 plus 12 is 6. And I'm going to preserve the negative sign that's outside. Okay, now I'm in echelon form. There's zeros below the main diagonal. There's a pivot in every column, so this thing's invertible, and the columns are linearly independent, and a bunch of other stuff, but all we really want right now is the determinant. So the determinant is the product of the main diagonal. So 1 times 3 is 3, times 6 is 18, so it's negative 18. So that's the basic idea on all of 5 through 10. Just reduce to echelon form. Keep in mind from way back in chapter 1, echelon form is not unique. If you had chosen maybe not to swap rows here, you would have gotten something different, but the diagonal would still have multiplied to 18. Or I guess if you didn't do a row swap, it would have multiplied to negative 18. Right? But anyway, you'd still get the same determinant. Okay, let's look at a few more examples. So 11 through 14 say combine row reduction and cofactor expansion to find the determinant. So basically what they're telling you here is be as efficient as you can. Save yourself as much pain as you can. And it's different for every one of these, but looking at 12, I already see if I did cofactor down the fourth column, I'd get a couple zeros, and that's fine. But let's be even more efficient, and let's say the more zeros the better. And I could work on this fourth column, but just for sake of illustration, I think maybe I'll work on the first column. So I'm going to start row reducing just by putting zeros in this first column here below the negative 1. So negative 1, 2, 3, 0. I need to add 3 of row 1 to row 2. So that'll be 0, 6 and 4 is 10. 9 and 3 is 12, and 0 and 0 is still 0. I also need to add 5 of row 1 to row 3. That'll make 0, 10 and 4 is 14, 15 and 6 is 21, and 0 and 6 is 6. And finally I need to add 4 of row 1 to row 4. So that'll be 0, 8 and 2 is 10. Was I doing 4? So 12, 16, and 0 and 3 is 3. Okay. So now I've got an even better column to do a cofactor expansion on. I'm thinking about how much more row reducing I want to do. I could just go cofactors right here. I'm not loving the idea of clearing out this 14 because that would require like negative 14 tenths times row 2 added to row 3. I might clear out this 10 though and make that one a 0. Just to give me one more 0, just because it's easy. Okay, so negative 1 of row 2 added to row 4. So 0, 4, 3. Could do a little more work if I wanted to, but I think I'm probably just going to leave it there. So let's go ahead and do a cofactor expansion now, and I am going to choose to expand down this first row that has all these beautiful zeros in it. So the plus minus plus starts with a plus here, so this would be -1 times the determinant of this 3 by 3. And again, for my outer layer, all the other cofactor expansions are 0. So all I'm doing is finishing off the determinant of this 3 by 3 on the inside. I put a 0 in that first column, so I guess I'll go ahead and use that first column again. And say it would be 10. When you cross off first row and first column, it would be 10 times, oh boy, 21 times 3 is 63 minus 24. It should be 39. And so then we'll have minus, from the checkerboard pattern, minus 14 times, and we're crossing out this row and this column now, so that'd be 36 minus 0. Okay, and now I'm getting to the point where I need a calculator. So let's see, this will be -1 times 390 minus something. What's 14 times 36? 504. And then 390 minus 504 is -114. So I think this whole thing comes out to positive 114. By the way, any good matrix calculator like Microsoft Mathematics or your TI-84 or 89 or anything else can do determinants. So feel free to check these. Obviously, you can check in the back of the book, but you can check them on your calculator as well. It's probably worth practicing just doing them on your calculator once or twice, just so you know the process. Okay, so the next set of homework questions give you this unknown 3 by 3 matrix whose determinant is 7. So we don't know what A, B, C, D, E, F, G, H, I are, but we do know that the determinant is 7. So then they say, okay, go ahead and figure out the determinant of these other matrices. And since we know what row operations do to a matrix, it's easy enough to say, hey, if they multiply a row by 3, that multiplies the determinant by 3. So the determinant of number 16 is 7 times 3, 21. On 18, what did they do? They swapped, it looks like they swapped rows a couple times. It looks like they swapped first row for second row, and then first row for third row. So they did 2 row swaps, which makes 7 into -7 and then back into +7. And for 20, what did they do? They added 1 of row 2 to row 1. So we know that doesn't change the determinant. So there you go. That's the idea for 15 through 20. I think you could be able to work the others out just fine. And I'm not going to do anything here. I just wanted to point out for 21 through 26, they're first of all saying use determinants to find out if the matrix is invertible. So keep in mind, see if I can pick the right layer. Nope. 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 Where was it? There it is. Okay, square matrix is invertible if and only if the determinant is not 0. So you'll just check the determinant here, find out if it's 0. If the determinant is anything besides 0, it's invertible. If the determinant is 0, not invertible. And feel free to use any of like row reducing or cofactor expansion, any of those methods to find the determinants here. And 25, 26, and 24, they're asking you to find if the set of vectors are linearly independent, which we know from Theorem 8 is the same thing as being invertible. So really they're just asking the same question in a slightly different way. Okay, so I think that gives you an idea of all of 1 through 26. I did, of course, assign you 27, which is a true and false. There's at least one fact mentioned in the true and false there that we didn't talk about in these videos, so you'll have to read back through the book to find that. And of course, with the true and false, you should always be making reference to where you found that particular answer in the book, or how you know it. Okay, have fun on 3.2 homework, and then we will be on to chapter 4.